Hi everyone, welcome to a new episode in the Multiverse video series. I'm Javier Luraski, and today we're going to learn how to train ImageNet with R. So this happens to be the culmination of a series of videos that we've been recording. The past 5-6 videos that we've done have all been related with how to train data sets in a distributed fashion. Using tools like TensorFlow, Keras, and R, obviously. And if you don't remember, I would encourage you that you take a look at our YouTube channel. Just go to MLverse and start with Introduction to Deep Learning, where we basically lay down the conceptual foundation that you would need to understand why and how distributed deep learning works. Then we move into the specific of using TensorFlow and R for distributed training. Then we introduce Spark as a way to make our distributed training workflows easier to manage. And more recently, we started working on porting the AlexNet model into R, which as a quick refresher, the AlexNet model is probably one of the most important models in the field of computer vision, since at the time it introduced concepts like convolutions and GPUs to the computer vision discipline that since then has grown to embrace deep learning and many other alike technologies. And the last video that we discussed was kind of like helping you get a machine in the cloud with a GPU. And we're obviously gonna need to make use of GPUs to train ImageNet, mostly because ImageNet, it's a data set that contains a huge amount of data. So it's not even possible just to train it with just one GPU. To the point of these series, we'll have to use multiple instances. So we're going to discuss that throughout this video. Just one caveat, this video is not meant to be kind of like, it's not trying to beat the accuracy or like the modeling or anything that other communities have done. We're mostly trying to communicate and show the tools that we would use to train ImageNet using R. So let's get started with that. And kind of like the first concept that we need to learn is, what is ImageNet? So ImageNet is just a data set, I believe was created by Stanford. And it's just a collection of images that are classified under a hierarchical taxonomy called WordNet, sorry. So WordNet, it's basically just a tree structure of nouns that describes those images that are present on the ImageNet dataset. Now, this doesn't sound that interesting until we realize that there's millions of images in ImageNet, and the size of this data set is about 300 gigabytes. So it's a huge data set, and myself, I don't actually have access even to like a 600 gigabyte disk drive, right? I have a MacBook Pro, so like there's no way that ImageNet is gonna be fit into my computer. So some of the techniques that we've been exploring on this last video series kind of like lead us to this, because one of the first things that we're doing on this video, or that I did before we started this video, is I provisioned a couple Google Cloud Instance machines. You can choose your own cloud provider, but in my case, I don't have kind of like just 8 GPUs or several machines with 8 GPUs each and huge disk drives lying around. So we'll have to make use of kind of like cloud computing, and we'll also have to get clever into how we deal with this data set and how we train it. But first things first, let's talk a little bit more about the data set. So even though ImageNet is kind of like the data set that is available, there's a few variations, and the variation that we're going to be interested in talking about, which is described in the Wikipedia page, is this variation of a challenge called the ImageNet Large-Scale Visual Recognition Challenge. And basically this particular data set or subset of data of ImageNet uses 250 gigabytes. So by all purposes, it's basically the same size as ImageNet. We need to use the same tools that we would use to train ImageNet. But the great thing about this particular data set is that it's available in Kaggle. And Kaggle is this well-known website for machine learning competitions. However, it also provides a lot of the data sets that are pretty much ready to use for those competitions. And one of the datasets that is available just there is the ImageNet Object Localization Challenge, which we can then download. Now, if you have followed these kind of like the series and the videos that we do in the RStudio AI blog or in the MLverse video, you're probably familiar with the pins package, which is currently an R package that allows you to cache, discover, and share datasets with different R users across multiple services. And one of the services that it supports is Kaggle. And it's supported as a board, as the Kaggle board. And basically what you can do is you can connect to Kaggle and either publish datasets to Kaggle and also retrieve datasets from Kaggle. And the pins package does this in an efficient way by connecting to the remote dataset and caching it and making sure that we're not re-downloading the dataset over and over again. So let's try to do that. And what we're doing here is I have a local, I have a remote instance, a few remote instances running Google Cloud with R and RStudio pre-installed. They all have multiple GPUs. They have a decent amount of memory. They have almost half a terabyte of space. I did have to consider configure solid state drive disks because that basically gave us an improvement when downloading and processing ImageNet. But basically, all we have to do if we're starting from scratch would be to register the Kaggle board. And for that, we first need to upload our API key, which we're doing. And then all we have to do is register the pins package and then register the Kaggle board. And as you can see here, now we have access to my current datasets in Kaggle. But what is most interesting is that we can also take a look, grab this dataset from Kaggle, and then we can use the pins package just to kind of like retrieve this dataset, which is what we're doing here. We're basically asking pins to retrieve ImageNet and then extract ImageNet. Now, I'm not going to run this particular code right now. But just to give you kind of like an overview of the work that was involved here is my first attempt when running this code, it took me about an hour to download and decompress ImageNet just because downloading 250 gigabytes can take a lot of time. And some of the hurdles that I hit in my first attempt was I wasn't using SSDs, solid state drive disks. So it was being quite slow. And I didn't have like a high-end computer with enough bandwidth, which in Google Cloud, by getting more CPUs, you also get access to more bandwidth. So those were two of the caveats. But once I was able to figure them out, we can pretty much run this code and it will execute in about 20 minutes, which is it's quite good. I think it can probably be optimized more. But then we're done with the download part of having ImageNet locally. So here you can see that we have our kind of like pins cache, and we've extracted ImageNet. And ImageNet is just basically this collection, as I was mentioning, of WordNet categories. And we can take a look at a few of them and see what they are. They're literally just images. This looks like a shark to me. This one. Shark again as well, I guess, maybe, and another one. And we could also take a look at the actual categories if needed. But this is all to say that ImageNet is just a collection of images. There's just thousands of images in each category, and there's thousands of categories. Now, in this particular case, what we're gonna do is so the challenge that we have is that while we have already downloaded ImageNet and it's kind of like local to us, and we can take a look at that, and why not? So while ImageNet is already local, if we're gonna be using multiple computers and if we're gonna be turning off and on and off the cloud instances, we don't want to be waiting 20 minutes each time just to download ImageNet over and over again. So I also found myself spending time trying to figure out if there was faster ways that we could download ImageNet to avoid having to have multiple computers, just literally downloading files and extracting them. and doing more productive stuff. So I end up using also the pins package to kind of like pre-process ImageNet. And what I did was the following. I registered a Google Cloud board, and I named it ImageNet, whatever. I created a bucket for it, and then I basically re-uploaded each of the categories that you can find here of ImageNet. I re-uploaded them as zip files, and you can do that with the pins package just by passing the zip equals true parameter. And it basically it got all the categories of ImageNet re-uploaded to, in this particular case, Google Cloud, which is the cloud provider that I'm using in this particular video. And once we have that, then it's really easy to, first of all, register the board, because now it's a public board and we can have access to the categories. So we can retrieve the categories. We just pin get and then the categories which we pushed. And then we can take a look, for instance, at those categories. Let's just do that really fast. And we were looking at the fifth instance in entry 1, 2, 3, 4, 5, which is not just a shark, but it's a hammerhead. So, you know, this particular entry of ImageNet is just representing a bunch of sharks that in particular are hammerhead sharks. And so our task would be to build a model that properly classifies these hammerheads, and not just hammerheads, but also the different categories, and do that in a distributed fashion. And again, like once we have that particular category, we can take a look at, you know, kind of like how one category looks like, which is just, you know, a set of images. And then what we can do is, you know, once we have all these data set, you know, once we have the entire data set partitioned in Google Cloud, what we can do to be more efficient is we can train the data set distributed by providing each instance running TensorFlow and their GPUs. We can provide a subset of ImageNet, which in this case, what we're running is we're just running 1/16 of ImageNet. And what we're going to do here is we're just going to partition it and get 1/16 of ImageNet. And then we're going to download all those categories in parallel. And this is to do that, we're using the call-R package just to make sure that all those files get downloaded in parallel. And from that, we can cut the time all the way down to 1 minute. So again, you know, like this feels a little bit pointless. You know, I spend a lot of time reducing the download speed and decompression of ImageNet from 1 hour to 1 minute by both using local SSDs, bigger machines, partitioning, and moving the data to my current data center. But all these things pay off, because now whenever we need to train ImageNet across multiple machines, we only need to wait 1 minute. We don't need to spend 1 hour waiting. And as you can see here, the data set is already downloaded. So we have 1/16 of ImageNet in this particular cloud machine. And then all we have to do is put it in a format that is friendly to TF datasets, and we're pretty much done with the pre-processing step. Now we can focus on pushing these to TensorFlow and processing these distributed. And for that, I think it might be worth just doing a quick recap. As I mentioned, this is a topic that we've covered several times on how to do distributed processing with TensorFlow. But if you need a refresher, you can go to tensorflow.rstudio.com and then go to the Advanced Distributed Training with Keras tutorial. Or you can take a quick refresher also on the tensorflow.org website. And here, you might remember from our previous videos that we used what we call the multi-worker mirror strategy. There's another interesting strategy, which is the mirror strategy, which allows you to distribute, to perform distributed TensorFlow work across multiple GPUs. But we're getting a little bit ahead of ourselves. Before we get started with training, we want to make sure that we actually have a GPU available. So that would be step one. And if not, you can take a look at some of our previous videos and just make sure that the GPU is kind of like available. And once you have your GPU available, what we want to do is, let's just make sure it's true. Yes, it's true. What you want to do is you want to install AlexNet, which is the port that we work on one of our previous videos to basically implement AlexNet in in R, which we currently have here, and then we can go ahead and train this particular data set, which again, like the great news here is that we're already training ImageNet. It just happens to be 1/16 of ImageNet across in our GPUs, but this is showing us a way of scaling this particular data set and the tools that we need to actually train in this particular, for this particular problem. Now, if we were to look at what are the particular GPUs that are being used in our training, we're gonna see our first problem, and is that running an NVIDIA SMI will show that only one GPU is being used. Which, I mean, it's great that a GPU is being used, but if we were to have 8 GPUs, we will only be using one GPU at, in this case, 40% usage in this particular case, which is not great. We want to be using all our GPUs. So how do we solve that? Well, we already pointed out or hinted out the solution, which is using the mirror strategy in when we're training with multiple GPUs. So let's go ahead and do that. So I'm going to stop this train. And what we want to do instead is we want to specify the mirror strategy while training. So let's just go ahead and do that. And if you were to be training your own model, you would have to recreate and recompile your Keras model. But we already pushed a little kind of like change to the AlexNet repo, which basically does that. It adds a new strategy parameter, and then all the strategy parameter is doing is when the strategy is given is creating the model and compiling the model into that strategy, which is the only change that you would have to do for your models as well. So here is being defined, and here when we compile it, we pass the model. And since we're putting all these within with block, it's basically specifying, it's basically letting TensorFlow know that we want to run this training in multiple GPUs using the strategy that was given. So let's go ahead and try to rerun this particular run using multiple GPUs. And we're also going to specify the parallel parameter. We're going to set it to 4. Now, this has nothing to do with GPUs, but rather with TF datasets. So TF datasets has a parameter that we can specify, which is the num parallel calls, which basically allows us to ask TF datasets to use multiple CPUs to load the data more efficiently into the GPUs while training. So again, that's another consideration that we can make use of. And then we'll just basically rerun our train. And what we should be able to see here is that, well, first of all, the training has started. And now we can also run NVIDIA SMI, and we can see that we have 2 GPUs being used, one with 50% usage and the other one with 27%. And again, this obviously changes over time, but we just have validated that we're actually training ImageNet across multiple GPUs. Now, the great news here is that we could, if in this case I provisioned a machine with only 2 GPUs, but there's nothing stopping me from provisioning a machine with, say, 8 GPUs. I would just rerun the same code, and now I would be using 8 GPUs to train this particular data set with the AlexNet model. Now, one of the questions that it's missing is, what do we do in order to scale beyond 8 GPUs? And for that, you already know that the answer, which is we can use multi-worker mirror strategy, which not only allows you to use multiple GPUs, but you can also use multiple instances with multiple GPUs each. And if we were to take a look back at that post from OpenAI, sorry, not OpenAI, but FastAI, where they presented training ImageNet with 16 instances and 8 GPUs on each instance in under 20 minutes, then we could follow a similar strategy by changing our TensorFlow code as follows. So what we would do is we would basically specify a TensorFlow configuration, which in this case basically sets, for the two instances that I have with 2 GPUs each, we would have to specify our IP addresses of where those machines are running, and our unique identifier per machine, and then the strategy. So in this case, we would change the strategy to multi-worker mirror strategy, and then we can go ahead and run retrain AlexNet with the distributed, fully distributed with multiple GPUs strategy. And again, like the only thing really stopping us here from scaling is, like the resources that we have available and the time that we have to kind of like create this infrastructure to let us train image models efficiently. Now, you might already know from one of our previous videos that while we could still potentially connect to multiple R instances and run this code across 16 different machines, this can be quite painful. So the first suggestion that I would have is that you probably want to create a script that both starts the machines in your cloud provider, retrieves the datasets using the pins package, and then trains using TensorFlow in a distributed fashion and retrieves the trained model. So that would be one approach. This is great, kind of like if you are sure what you're doing. But one of the challenges when training a model in a distributed fashion is that, most likely it hasn't been trained before. So you probably want to also change the model and change the number of instances and, change different parameters and pre-process the data. And for that, you can use things like Spark. So we would replace this code. Well, we wouldn't replace it, but we would wrap this code using barrier execution, which we went into details in the video on training TensorFlow with Spark and R. So again, like what is great about this particular example is that there's nothing preventing us from training ImageNet. Really, the only two things that are blocking us is time and money. And time in this case of creating a better infrastructure that allows us to easily scale from 2 computers to 16 computers. That's part of it. And that also, like the other restriction that we have is just how many resources do we need to invest, do we want to invest to train ImageNet? Now, in my particular case and circumstances, I don't think it's worth it to train ImageNet just for the sake of training ImageNet. But you might have a particular use case that does require you to train not ImageNet, but perhaps a different data set at scale. And really the only restriction there is the time and resources that you want to spend into building the infrastructure to train ImageNet. But, hopefully this video presented the tools that are already available for the R community to train ImageNet and large scale data sets at scale. I would love to see if someone from the community wants to contribute to AlexNet, or in general take this approach a step further and actually use ImageNet and concepts similar to this one to also train other data sets at scale with TensorFlow, Spark, and R. I hope this video was useful, and we'll keep in touch.